We're in part 3 of chapter 5, sampling distributions, and we're looking at the distribution of the difference between two sample proportions. And of course, we do that when we're trying to make an inference on the proportion of two independent populations. Studying the sample distributions allows us to make, valid inferences. Now, let's look at the distribution. First of all, let's assume that we take independent random samples, size 1 and 2, drawn from two populations. Now, we have to assume that the two population proportions are P1 and P2. Whatever they are, they're usually unknown. And we take a sample, of course, N1 and N2, and we calculate the proportions, P1 hat and P2 hat. These are estimates of the population proportions, of course. And then let's study the difference between these. And it's going to be shown that it's approximately normal, and it has a mean and a variance. So the way that we describe this, it's the mean, that's what mu is, of the difference in sample proportions. So the mean and the difference of sample proportions is just the difference of the true population proportion. So it's an unbiased estimator of that difference. The variance associated with the population or the difference in sample proportions can be shown to be this. It's really the addition of the two sampling variances. And then, of course, we have to assume N1 and N2 are large for this to be approximately normal. And there is a little requirement that N1 and N2 are sufficiently large. So what does that mean? Well, we look at each of these quantities here, and they have to be greater than 5. And if that's the case, then this is a pretty decent approximation. So the difference in sample proportions is approximately distributed with the normal random variable and this mean and this variance, which of course are given up here. Now, if you only have a CDF table in the back of a book, then we have to convert this to a standard normal. So we take that quantity, which are our random variables, subtract the population mean, divide by the standard deviation of this distribution, and then our new random variable is a z, which is distributed as a standard normal random variable. So let's look at an example. So in endometriosis, it's a disorder in which the tissue, similar to the tissue that lines the uterus, grows on the outside of the uterus in places that it doesn't belong. It's a very painful disease. Studies show significant risk of endometriosis among women who began menstruating before the age of 11. So let's sample two populations, one where the women began menstruating early, and let's assume that this group develops endometriosis with probability 0.55. And notice that we're assuming that's the population parameter. And then the second population is women that menstruating at a normal age. And let's assume that this group develops endometriosis with a probability of 0.1. Again, we're assuming that's the population parameter. So let's take samples of 175 from each population. They're independent samples because these are independent population. And we want to study is the population or the probability that the difference in sample proportions is less than 0.3. Now, first of all, is a normal approximation to the difference of sample proportions, are the sample sizes large enough? So we look at these differences. So this is N1, P1, and it's greater than 5. N1, 1 minus P, greater than 5. And then we check all these conditions. And since all are greater than 5, then we can use the central limit theorem to estimate this probability. So this is the probability of interest, that the difference in sample proportions is 0.3. And we could just calculate that in R, but let's convert it to a standard normal just so we can see it. So If we subtract the mean from both sides, so what's this quantity and this quantity, and we divide by the standard deviations, then this left side is a z random variable, and of course that reduces to this. And since it's in CDF format, we can put it in this notation, which is capital Phi, which stands for this CDF for a standard normal random variable. And then this is the probability. Now, to do this in R, we can just take that number and put it in P norm. P stands for proportion, so it's the CDF of a standard normal, which is what this value is. So that's the quantity. Now notice that there's no additional parameters in here. Like, since there are none, it's assumed that the mean is 0 and the standard deviation is 1. If you leave it blank, that's what it is, and that's the mean of a standard normal is 0 and the variance or standard deviation is 1. We could just put this quantity in R. So we want to be, what's the probability this difference is less than 0.3, so we put 0.3 here. The mean, of course, is the difference between P1 and P2, and the standard deviation is the square root of the variance, and then when we plug it in, we get this, and it is the same. Okay, so next video, we're going to look at chapter 6, which is estimation.